In this video, we're going to continue our conversation about differences between means. And actually, before jumping into where the population standard deviations are unknown, let's go on and talk about the hypothesis testing to close out what we were doing earlier with the confidence intervals. So for hypothesis testing, I think we've already talked about this, but generally the form of hypothesis tests are going to be the point estimate divided by the standard error, and then we're going to compare that to a critical value. And I apologize for my terrible writing. Typically, this is right if we're comparing the difference to 0. So if we're asking the general, is there a difference between the two values question. So actually, to write it in the notation that we have here, this would be a piece that's also included. But know that when the difference is 0 that we're comparing to, this just kind of goes away, and then we have point estimate divided by the standard error. So this is why, I know we've talked about this before, but this is why our hypothesis tests are so closely related to our confidence intervals. Now, just like we had before, we've got upper and lower tail tests. Typically, these null hypotheses are written with equal signs, not the opposite sign, but whatever. Then the alternatives are less than, greater than, or not equal to, depending on the direction of the test. Again, please note, if you change the order of the two groups, the order isn't set in stone. So if you change the order, the sign here is going to change. So this one is saying, I think, the mean of group 1 is smaller than the mean of group 2 is if we're comparing to 0. This one is saying I think the mean is larger, but if I change which group is which, so think about what I just said. Mean of group 1 is smaller than mean of group 2. Switch which one's which. Males less GPA than females. If I switch and put females first, females would have more GPA than males. So if males is smaller, then if females go first, females has more than males. So the direction actually changes. If that doesn't make sense, you can replay it if you want to wrap your head around it. All I'm trying to say is set which group you want to be group 1 and group 2, and then keep that the same through the whole problem. If you change it in the middle of the problem, you're going to run into issues. So try to keep it consistent through the whole problem to make sure your answer is right. And I guess the last thing on that, it really doesn't matter. It doesn't matter which group you choose to be which. Just keep it consistent throughout. And again, that's why I like the little like to use in subscripts that are meaningful for my problem instead of subscripts that are kind of generic. So in this case, again, we've got our test statistic, we've got our point estimate minus this difference. And again, usually that's 0. So usually, actually in some textbooks, they don't even write this. I like that we have this though, because we don't always compare to 0. Almost always we do, but it's really good to know how to not do. And it's a really simple thing to not compare to 0. You just subtract the number you want to compare to when you're calculating your test statistic. You divide by that same standard error we had before, and that's how you get your z-test statistic. So here we're going to use an alpha equals 0.01 rate. So this is different than that 0.05 rate. Because we're using a different confidence level, we can't use that 95% confidence interval to do the test. The confidence interval confidence level of 95% has to match the alpha level if you want to use a confidence interval for hypothesis testing. In this case, it doesn't, so we need to redo the test, or we need to construct a test in the first place. So here we're going to say I think par is bigger than RAP, and I think this was talked about in the problem. Yeah, we have, is the par greater than the mean of the RAP balls? So I say I think par, I'm going to call that group 1, is bigger than the mean of RAP. So group 1 minus group 2 is a positive number. Note that, again, you can start, if you wanted to, if this is easier for you, you can kind of start by writing it like this. I think that group 1 is bigger than group 2, and then you could subtract group 2 from both sides, and that's how you could get this. So that's an option too, if that's an easier way for you to see it. Sometimes you'll see textbooks that write it this way instead of that way. I actually prefer this. I like this, and the reason I like this is because it matches up with how we get that point estimate. So whatever you'd like to do, if you want to start here to move there, or if you just want to jump straight into this alternate hypothesis, that's just fun. So we calculate the test statistic. Just plug in our numbers from previously. We get 6.49. Now we're going to use this alpha of 0.01 to calculate our critical value. Now this is an upper-tailed test. Why is this an upper-tailed test? Because I'm looking at a greater than. I'm asking if this difference is greater than 0. And I'm only looking in that greater than direction. So an upper-tailed test. So I'm going to look on my critical value. So I'll start with the critical value approach here. Sorry. Look on my critical value. I find that the z-value is 2.33. Compare the test statistic to 2.33. Find that 6.49 is bigger than 2.33. Then I reject the null hypothesis, and that is the sample evidence indicate, or we have evidence that the driving distance of the balls from par is bigger than the driving distance of the balls from rep. And again, this is not the sample stuff that I'm talking about. The sample is what gave us evidence. We have evidence that the population, that all of the golf balls on average from par that our sample is representative of, is better than all of the golf balls from rep on average that the sample is representative of. So this is the cool part, again, is I can use a few hundred tries on a Sunday afternoon, and I can get a good feel for the fact that I want to be using par golf balls if I want to drive further. So the p-value approach, I can use R to calculate the p-value. The p-value is very small. Now remember what I do with the p-values, I compare it to my alpha. So alpha is 0.01, p-value is 0.00001. So the fact that the p-value is smaller than alpha, we reject the null hypothesis. So we can say that we have evidence that the par golf balls is greater than the rep balls. Now notice in this statement I have that at the 0.01 level of significance. This is true for both this, the p-value approach, and the critical value approach. So you can always drop this in. Sometimes I'll add it in parentheses at the end using alpha equals 0.01 in a conclusion section. Sometimes that's how that's included instead of this at the 0.01 level of significance. Actually, a lot of times this is included in research. Is we have a method statement in our research paper, or just at the beginning of a research brief, and we declare there that we use this level of significance throughout the rest of the research paper, so we don't have to write this for every question. So often that's what's done to address this. Excuse me. So let's see, one more thing that I wanted to talk about here was how we tend to report really small p-values. So typically there's a professional standard that if your p-value gets small enough, you don't write out that p-value. So this p-value might be 0.0000001, and it becomes kind of tedious to write all that. What we do instead is we tend to write p is less than, and then whatever level we tend to write. APA is often 2 digits, less than 0.01. Actually, you'll also see in APA 7 less than 0.001. So maybe this one is a better one. So if it gets, if it's bigger than 0.001, then you write p equals whatever that is. If it's smaller than p 0.001, then you just write p less than 0.001, and you don't worry about all the remaining values. So this one goes out a little bit far. It's kind of ridiculous a little bit. So maybe don't write out 3 zeros after the decimal place. Maybe just 2 is good enough. And in fact, in a lot of research papers, I write just 1. So it really depends on the type of research you're doing. But this is extraordinarily common, and that's to prevent us from getting a ridiculous number of zeros in the write-up. All right, so let's jump right into what we do when the population standard deviations are unknown. Now, I'm going to jump right in here because this is going to be the exact same thing that we normally do, that we did last time when we were talking about confidence intervals and hypothesis tests, in this case with the single sample. But now we calculate the two standard deviations as the estimates of the two population standard deviations. So we've got two samples, standard deviations. We again replace z with t. And actually, for the equation, this is all we need to do. So if you look at our confidence interval equation, the point estimate's the same. We replace z with t, and we replace sigma with s, and ta-da, our equation's the same. The trick with this comes with the degrees of freedom calculation. Now, there's many ways you can do this degrees of freedom calculation. This is called the Satterthwaite approximation and is probably the most accurate way to try to calculate this. The book rounds correctly on this. Typically, if I'm doing this professionally, I'll round down. I'd rather be a little bit statistically conservative. Again, that's not politically conservative. Statistically conservative is where we have a lower chance of a type 1 error, and rounding down the degrees of freedom instead of correctly rounding the degrees of freedom reduces the chance of type 1 error somewhat at a reduction of statistical power. Or at a slight increase of a chance of a type 2 error. So in this particular case, you can calculate the degrees of freedom here. Other ways to calculate the degrees of freedom, maybe the most common other way, if I'm doing like a real quick slapdash job, would be to use the smaller of the two groups, sample, and then calculate the degrees of freedom from that. So in this case, let's say I had a group of 30 and a group of 50. I might use the 30 group and then have take that 30 minus 2, and I'd use 28 as my degrees of freedom. So that would be one way in which you could do that quickly in slapdash. In this class, we'll use the Satterthwaite approximation. It's what our textbook does. It's some good practice working with a yucky equation. Order of operations here, you take your sample standard deviations, you square them, then you divide everything, then you do all the squaring of everything, then you multiply your 1 over n minus 1 times that squared value, 1 over n minus 2 times the squared value in the denominator. Your numerator should already be set, and then you've got one value divided by something plus something, so you do your addition and then you divide. So that's your order of operations here. If you plug this into a calculator, into R, be very, very careful about the order of operations in your parentheses. You're going to have a whole ton of parentheses. That's okay. Just pay attention to it. And you're always welcome to break it down in pieces. Actually, sometimes with the long equations like this in R, I'll have a numerator and I'll just call it num, and denominator, I'll call it denom, denom. So that I don't have to do quite as many parentheses for a single thing, and then I'll do the degrees of freedom as num divided by denum. Another final thing, again, the book rounds the degrees of freedom correctly. In R, you can hand R fractional degrees of freedom. So if you're using R or another statistical analysis software that can handle that, just take your actually calculated degrees of freedom and you can plug it in to get a perfect answer. That's exactly right for that given t. It'll calculate the integral, again, with a fractional degrees of freedom. It's pretty cool. All right, so we're comparing two different cars, it looks like. Comparing miles per gallon performance. So in this first class of car, I've got 24 cars. In the second class, I've got 28 cars. I've got my mean miles per gallon and the standard deviations of miles per gallon for each of my samples. So I've got the sample size, sample mean, and the sample standard deviation. Again, this is how we almost always conduct comparisons of two groups. Some days you may be handed the actual data and you'd be expected to calculate these values for the data. And that's okay. You can do that. You can find the mean of a data set and the standard deviation of a data set. The trick here, though, again, is we calculated this value from data, or these values from data. Nobody handed us a population standard deviation that we had to assume was right. We actually found this from data. So this is a typical problem that we could actually do, and we could actually help somebody out with something like this. Um, and again, this is why I like this is where we start getting into cool stuff because we can actually use data to get an answer. It becomes a little bit less abstract that way when we're assuming we know stuff. We don't have to assume anything here. While we do make a couple of assumptions behind the scenes, but largely we don't have to assume any numerical assumptions. So we want to create a 90% confidence interval for the difference between. We're going to use M for the first group and J for the second group. Again, if I were writing this, I might write mu sub M and mu sub J and X bar sub M and X bar sub J, just so I don't get confused. But in this case, we'll just keep it generic and have 1 is going to be the M group and 2 is going to be the J group. And again, it doesn't matter how you assign these. All that matters is that you keep it consistent. So actually right now, go in and pause the video. Give this a shot on your own. See how you do. Start with the calculation of the degrees of freedom. That's a big yucky equation, but do your best. Again, we'll round correctly to match the book here. And then go on to your calculation of the confidence interval. So pause the screen, give it a shot. All right, so for the degrees of freedom, plugging all this nastiness in, I get 40.59 to within rounding error. Again, as you round the squares, you may get something a little lower, a little higher. Again, for correct rounding, we'll go to 41. Typically, again, to be slightly conservative, I'd go down to 40, but the book does it this way, so let's stick with that for this class. Alpha over 2 is 0.05. Now, this is important to note. Alpha, in this case, for a 90% confidence interval is 0.10. 0.10 divided by 2 is 0.05, so don't get confused. 0.05, which sometimes is alpha, in this case is not. This is alpha over 2, because in this case, on the previous slide, we defined alpha to be 0.10. Degrees of freedom, correctly rounded, was 41, and then I used these two values with t to calculate my t value of 1.683. So I did all that just so I could find this critical value, but my point estimate and my standard error are just the same as I did before, except now the point estimate's exactly the same as I did before. I just plug in the sample means. The standard error is the same as before, except now instead of assuming that I know sigma 1 and sigma 2, I actually calculated the sample S1 and S2, so I didn't make that assumption. I used data for everything I got here and got this calculation. So that's how I get my standard error. Plugging it all in, I get 2.5 as my point estimate, plus or minus this margin of error of 1.051. And that gives me a reasonable range of values being between 1.49, so about 1.5 and about 3.5. So a reasonable range of values is that the difference is 1.5 to 3.5 miles per gallon. And that's good to know. So looking at this, let's see, I think M cars was group 1 and J cars was group 2. So this is positive. That means the first group is bigger than the second group. So the first group has more miles per gallon than the second group. This difference, the 0 is not in this interval. Again, 0 would represent 0 difference. This is the size of the difference. So because 0 is not in this reasonable range of values, 0 is not considered a reasonable value. So 0 difference is not considered reasonable based on this data. Reasonable values would be 1.5 miles per gallon to 3.5 miles per gallon. So in this case, it looks like M-Cars is going to have a little bit better performance, at least in terms of miles per gallon. How much better? Is this meaningful? These are questions that it really depends on your context. If I'm just driving it around town and I don't put a whole bunch of miles on it, maybe 1.5 to 3.5 isn't really meaningful. Maybe if I'm driving mid-range, 3.5 would be meaningful, but maybe 1.5 wouldn't. So I'd need to do another study to narrow this in even more and recall how we narrow this down is by getting a higher sample size. We can get more and more precise and narrower estimate with the same type 1 error rate. And it also could be that if I'm driving a long distance, anything in this rate is going to be just fine. So so we can say this is statistically meaningful, statistically significant, because 0 isn't in this interval. But as to whether it's practically meaningful, it really depends on the context of the situation in which we're interpreting it. And I just gave you 3 different situations in which this could be interpreted as not meaningful if I'm staying in town, potentially meaningful if I'm driving a mid-range, or meaningful from the bottom end to the top end if I'm driving long range. This also highlights the benefit of confidence intervals because I can see what the bottom and the top end is. It could be that even if I'm driving long range, this 3.5 miles per gallon isn't enough or isn't meaningful enough. What does enough mean? Well, maybe the M cars are more expensive. Maybe the amount of money saved on gas for a 3.5 miles per gallon better rate isn't worth the additional sticker price of $20,000 for M cars. Again, all of this depends on the context, and this is why interpreting statistics sometimes is pretty tricky. But it's also why I like confidence intervals for interpretation, because I can go back to the client and say, it could be 1.5, it could be 3.5. All of these are reasonable. My best guess is somewhere in the middle of those, but these are reasonable values out on the edge. So are all of these meaningful? If only some of these are meaningful, maybe we have to do a different study to narrow in and see which edge of the interval it falls into, or if it falls right in the middle. All right, so jumping into hypothesis tests, again, this is going to be very similar to what we had before. All the hypotheses are going to be exactly what we had before, and the structure of the hypothesis test is, the test statistic, is going to be what we had before. Our test statistic is T now because we're comparing to a T distribution, but everything's the same except the sigmas are replaced with S's. Using this, we're going to do a 0.05 level of significance test. Same thing we did previously. So again, we're going to have group 1 be the M cars, and we're seeing if M is bigger than J. That's our directional hypothesis that we have for this particular situation. Plugging in the values just into the equation, I get a T value of 4.003. Again, I need to calculate the degrees of freedom here so that I can find my critical value to compare to, or so that I can find the right line on the table if I were using a T distribution, or figure out what to plug into R if I'm having R generate the T critical value, or R generate the P value. So for all these, I need to find the degrees of freedom. So I'll go on and calculate that. It's the exact same as we had before, 41 value rounded up. Or rounded correctly. And again, I'll interpret the critical value approach first. So for alpha equals 0.05, degrees of freedom 41, my critical value is 1.683. Again, we saw this before. Now, don't be thrown off. We saw this for a two-tailed confidence interval with alpha equals 0.1. This is for a one-tailed test with alpha equals 0.05. So it shows how these two are related, and I apologize about this. That can be a bit confusing, but just walk through it a couple times until you get it if that doesn't make sense. So we'll reject if it's bigger than this value. Again, this was an upper tail test. We do see it's bigger than the value. So we have evidence that the miles per gallon of M cars, again, the population of M cars, all M cars on average, have a better miles per gallon than all J cars on average. Again, that these samples were representative of. Going back to the p-value, I can calculate the p-value directly. So I'll calculate the p-value in R, or if you wanted to use a table, you could say the p-values between these two things. That's kind of a yucky and disgusting way to do it. So I'd calculate the p-value in R. I do not like this representation of a p-value. What I would write is something like the p-value is less than 0.01, because 0.05 is less than 0.1. Or let's say I knew the p-value was equal to 0.0043. Then I would write then I would write P is equal to 0.004. So I'm either going to use this less than notation if I only want to go out to 2 decimal places, or if I want to go out to 3 decimal places, I'm going to use the decimal place notation and write it out exactly. If it's less than 0.001, then I'm going to write that. P is less than 0.001. If it's equal to 0.001, I'm going to write P equals 0.001. So just follow that kind of standard rule that we described previously. And again, in this same case, we've got the evidence because P, however you represent this, P is less than 0.05. We reject the null hypothesis. What does that mean? We reject that there is no difference. Null hypothesis is no difference. Nothing's going on. And we reject no difference, which means we think there's a difference. There's evidence to believe that there's a difference between the population of cars. And I can't say this enough, but recall that the null hypothesis was about population mu values, not sample values. So we reject no difference in the population values, which means we think there's a difference in the population values. So in this case, we think that the population of M cars has a better miles per gallon on average than the population of J cars. And again, this is why stats is cool. You give me some data from a sample, and I can tell you decisions or probabilistic decisions, decisions with evidence about not just the data you handed me, but all of the values that data represents. And that's pretty cool. All right, so in the next video, we'll jump into this, the matched samples. It's a pretty cool design. I like this a lot. We do it all the time. So in this matched samples design, it'll be our first dependent samples value. You could call it a very, very introductory time series or longitudinal if you want. I'm actually doing a study with something like this right now. So we'll jump into this in the next video and discuss how do we analyze data with a matched sample and what even is a matched sample.